Okay, everyone, thanks for coming. Let's get started for this week's seminar. So the C3AI DTI mission is to attract the world's leading scientists in a coordinated and innovative way to advance the digital transformation of business, government, and society. And our weekly seminar especially focuses on the interdisciplinary effort that joins effort from machine learning, computer science, engineering, and operations research to tackle problems that have high societal impact. So I want to pause here to sincerely thank our academic partners, the computing support, as well as the industry partners. So we're approaching the end of this series. The theme of this semester is the incentive design and learning for societal systems. We have two more talks this semester. Today is from Professor Nikhil Garg, and next week we will have Qingmei at Berkeley to share his research. We have had wonderful talks in the past weeks of this semester. If you have missed any of these and you find it to be interesting, please go check our website. We have all the information, including the slides and YouTube recording on both the website as well as the YouTube channel. Okay, so today we're very excited to have Professor Nikhil Garg to share his research on auditing and designing for equity in resident crowdsourcing. Professor Nikhil Garg is an assistant professor of operations research and information engineering at Cornell Tech in the Jacobs Technion Cornell Institute. His research interest is applying algorithms, data science, and mechanism design to the study of democracy, markets, and societal systems. He received his PhD from Stanford University and has spent considerable time in industry most recently. He was the principal data scientist at PredictWise, which provides election analytics for political campaigns. Nikhil received the Inform's George Danzig Dissertation Award and an honorable mention for the ACM's SIG-Econ Dissertation Award. So as usual, the presentation will be about 50 minutes and we will have the 10-minute Q&A at the end, but feel free to post the questions in the middle and Nikhil will try to answer them during his talk. And without any further delay, Nikhil, the floor is yours and you can share your screen now. Thank you.
Great, thank you. Larry, maybe we can start the poll while I'm sharing my screen and so on.
Do you see the poll?
Yes, I do. Thank you. Okay, great. Yeah, thank you for the introduction and for having me, Manshi. I've been going to the seminar series all semester, and it's really great to be here, and to join all the other really great speakers who have spoken so far. So I'm Nikhil, and today I'm going to talk about specifically one paper, but more generally a broader research agenda that I've been working on in the last year and will be going forward. This is the broader agenda is joint work with quite a lot of people, but the paper that I'm going to mention today is with my PhD student, Zhi Liu, who's also at Cornell. And special thanks to the Urban Tech Hub at Cornell Tech, which provided some of the initial funding, and then the New York City Department of Parks and Recreation, who's been a great partner in this work. And so can we maybe close the poll and see the results? I actually don't know where the poll went. Oh, okay, great. Okay, great. I see the result. Okay, so most of you, it looks like, do not know what the what 311 systems are, which is great, or maybe partially great. So hopefully, first thing I can teach y'all today. So in many cities in the United States, there's more generally across the world, in the US, it's called 311. There's a phone number that you can call to complain to the local government. And so you can, in the US, you call 911 if you need a police officer, an ambulance immediately. You call 311 often to complain about everything else. So potholes, bed bugs, if a tree is about to fall down in a power line, sort of graffiti, noise complaints, all sorts of things. And these are absolutely massive systems. So for example, New York City's 311 system received about 2.7 million requests last year. And it's not just a way to complain. It's easy to be cynical that these are just ways to complain, but this is actually how a lot of work gets done in government. So for example, this is New York City has about 700,000 trees that are on the street. So not counting trees in parks, for example. Maybe I'm about to offend some vision deep learning people here, but it's like virtually impossible to do active surveillance on all of these trees sort of technologically, or through government employees. You almost definitely need people to complain about problems when they come up. And so what is the general pipeline for people complaining about problems to actual work getting done? At some point, an incident happens. So here, let's say a tree is about to fall down. And then at some point after the incident happens, hopefully we'll get a 311 report generated, either through a phone call or an app or so on. And this is, someone like you or me just like calling and telling them that this incident happened. And so, for example, the subunit of the Parks Department that we're working with receives between 70 to 100,000 reports a year. And the department in reaction is going to inspect a subset of the reports, by which I mean they're physically going to send out a forester to look at that, to try to find the tree that someone complained about, and then to run an inspection and then to log what happens. And this happens in our data set about 2/3 of the time. And then about half the time that a forester physically goes out and does an inspection, they end up scheduling a work order. So they end up submitting an order for a different maintenance crew to come around at some point in the future and to do actual work on the incident. So, fixing the fallen branch, or, treating the tree for disease, or if it's a pothole, filling the pothole, or things like that. And so what the research agenda that we're on is, how do we first understand or audit this entire system, for both how efficient is this entire system and how equitable is it? And then how do we improve these processes? So how do we help improve the processes of government agencies for both efficiency and equity objectives? The paper I'm going to talk about today for the majority of the talk is just about the first part of this pipeline. So how do we understand reporting behavior for an incident happening to a 311 report being generated? Why is this important? Is because if we have disparities or inefficiencies in this first stage in terms of who's reporting problems, then there's going to be downstream disparities in what work gets done. And this is what I'm going to focus on for the most of today's talk. At the end of the talk, I'll zoom out again and sort of talk about some ongoing work about the rest of the pipeline. Are there any thoughts or questions so far? One thing I did want to mention is I do see the chat and the Q&A, so feel free to type questions into the Q&A, and I'll just I'll answer them as convenient. Okay, so for the majority of this talk, I'm going to talk about this paper, Equity in Resident Crowdsourcing, Measuring Underreporting Without Ground Truth Data. This is joint work with my PhD student, Zhi Liu, and the paper's online if anyone wants to see it. Okay, so what do we do in this paper? We try to tackle the following statistical challenge, which is, how do we distinguish between underreporting and neighborhoods truly having fewer problems? So as a reminder, we're just thinking about the first stage of this pipeline, an incident happening to a call being generated. And so how do we think about differential behavior and who ends up reporting and how late they end up reporting? And this is a hard problem because by definition, we don't observe data on the missing reports, right? The entire reason these systems exist is because agencies don't have a sense of the ground truth unless a report happens. And so maybe another way to say it is if a tree falls in the forest and no one reports it, the city doesn't know about it. And maybe as a visual example, suppose we have two neighborhoods, one with, had 10 incidents about trees, so 10 trees fell down, and another neighborhood that had 5 trees fall down. In the first neighborhood, only half the incidents got reported, but in the second neighborhood, they all got reported. Then to the agency, these two neighborhoods are going to look identical, right? And they're both going to have sort of 5 of their trees fixed. But then we're sort of one of the neighborhoods is left sort of with less work being done than they need. And so this is the type of thing that we want to detect. The problem is we don't observe this 10 and 5. We just observe how many got reported. And this is sort of this general problem of not knowing the ground truth is a fundamental problem that's across many contexts that we care about. It's often called the benchmark problem. So in policing, we might care about sort of auditing inequitable policing, but then we need to distinguish between sort of heterogeneity in crimes committed versus inequitable policing across contexts. In ecology, for example, often we care about sort of counting how much of a species there is in an area, and we often need to correct for recording effort. So how much did we actually try to find sort of species in that area? And like how easy was it to actually find species in that area? And the standard way to do this is to try to separately get an estimate of the ground truth that doesn't depend on sort of the reporting behavior. So try to train some sort of model to answer the following question. How many incidents of each type, for example, hazards, trees that are cracking the sidewalk, requests to prune the tree, and so on, how many of these requests do we expect to see in each neighborhood, right? And try to get an independent estimate of this that doesn't depend on your reporting, the reports that you see. And there's a few ways you can go about trying to do this. For example, you can go out and walk the streets and try to, get it just like do an active walking of the streets to try to get a snapshot uncensored view. You could also construct all sorts of proxy measures. For example, the number of trees, their size, the species, and so on, and then train machine learning models to sort of predict how many types of requests you might need to see, you might expect to see. I'm not going to talk about this too much, but it turns out that this is a quite challenging method to do, right? So even if you go out and walk the streets to get a snapshot, so first of all, this might be expensive, but second of all, even if you succeed, you might not be able to you might not be able to sort of get measure reporting delays, which also, as I'll see, ends up being important. And so the question we want to answer in this work is, can we measure this underreporting? So distinguish between this half reported and all reported settings without any notion of the ground truth data. And the key idea that we leverage is what's called the missing species idea from the empirical Bayes literature, which is that we can leverage the rate of duplicate reports about the same incident to identify the reporting rate conditional on the incident having occurred. In our setting, there's an additional challenge on top of the classic missing species idea because we don't have a static set of incidents. We have incidents happen and a tree falls down today and then they get fixed either by the department itself or by someone else. And so now we care about not just sort of identifying the number of incidents, but we care about reporting delays. And I'll sort of formalize all of this in a model in a little bit. Okay, and so in the work, we flesh out the statistical method to capture reporting behavior without ground truth data. And then we apply it to understand reporting behavior of street tree incidents in New York City over 3 years. Are there any thoughts or questions so far?
I think there is one question on the.
I'm not sure it's a real question.
Okay.
Yeah. Yeah. Okay. So there's so we're not the first ones to think about understanding 311 systems or co-production systems. A lot of folks, especially in the political science and sort of administrative sort of studies communities, have tried to answer this question, and they primarily do so using proxy ground truth methods. And we end up showing in the paper, I'm not going to talk about it today, that our method, which we have confidence in, actually ends up giving very different answers than proxy ground truth methods, at least some of the time. And I'm and maybe more broadly, methodologically, we connect to, like I mentioned, sort of these ideas in estimating the prevalence of species, and more broadly, Poisson rate estimation methods. Okay, so let me dive into the model. So the data generating process is as follows. We're going to have an incident type theta that encodes geography and incident characteristics. So when we actually get to the data set, theta can be sort of the characteristics of an incident that the reporter reported. So things like, did they register it as a hazard? Did they say it was like a pruning request, or so on? It can also be characteristics that the forester who went out and inspected saw it as. So what is the true risk level? What is the size of the tree? What is the actual species, and so on? And then we're also going to have it encode geography, so very precise neighborhood that the tree is in. Okay, so we're going to have some type theta. And then we're going to say that incidents of type incidents of type theta are going to occur according to some process, big lambda of theta. And we're going to make 0 assumptions on this process. So it doesn't have to be Poisson or anything. And so, okay, so in this timeline at the top, I'm going to sort of lay out the lifeline of one incident. So at some point, the incident occurs according to this process. And then we're going to say that people report this incident according to a Poisson process with rate little lambda of theta. And so again, I'm not going to make assumptions about what kind of Poisson process. It can be inhomogeneous over time if we want. And so, for example, with this incident, let's say we observe a first report of this incident at some time after the incident happened. And what's crucial is this is the first time that we observe this incident. The first time that in the data set and as the agency knows that this incident exists is when it was first reported. And then, at some point later, we're going to get a second report and a third report. Okay. And so at some point, this the agency might also inspect this, inspect this incident. And so in the timeline, we're going to, just draw a purple bar for when the agency inspected the incident. And this is also observed in our data set, since we got internal administrative data. And then finally, at some point, the incident is going to die. It's going to be fixed by the agency or by someone else. And there's all sorts of neighborhood groups that go out and resolve problems on their own. And so we're going to model this as unobserved, even though it ends up being partially observed. Are there any questions on this, sort of high-level data generating process? So I see one question in the chat. Yes, certainly this is, a stylistic model of the world. At the moment, I haven't made any super strong assumptions, right? So sort of maybe the strongest assumption is that that people report the incident according to a Poisson process, by which I mean just reports are independent to each other, right? So conditional on one report, that doesn't tell you anything about when we're going to receive a second report. conditional on the process. Now, later on, when I actually get to the data component, we are going to impose more assumptions on sort of what we actually try to estimate. And there are going to be some some stronger assumptions there. Okay. Are there any other questions? I'm happy to pause for a second.
Do you mind if I ask a question?
Yeah, of course.
Yeah, so let's say there is an incident of type theta that was reported and then inspected and then fixed. So does it affect how likely the next incident pops up of the same type in the same area?
So that's a great question. So yeah, okay. So so at a high level, you might be sort of concerned that happens, right? Is sort of if I fix a tree in the location, then sort of that tree isn't going to sort of have another problem for another year or something. Yeah, so I mean, in theory, that certainly could happen. I would suspect that's rare. I mean, like sort of, yeah, I mean, okay, so let's just say it could happen. That doesn't affect anything in our, we're not going to make any assumptions about the incident occurrence process big lambda of theta.
Okay, yeah, that makes sense. Thank you.
But yeah, that certainly could happen. Maybe a more interesting question sort of in our model is what happens if lambda, if that affects little lambda of theta, right? Is sort of people see that the government is doing a really good job in their neighborhood, and so they start making more complaints. So we don't do like sort of in the actual empirical estimation, we don't actually sort of track like time varying lambda of theta, but sort of in theory, one certainly could. Okay. And so our research question is, how does this reporting process depend on the type, right? So how much does like how quickly people report depend on the type of incident? And so like, why is this important? If you have a reporting delay, so if it takes longer for someone to report an incident, then that's directly going to translate into delays in inspections and like the report getting fixed and the incident getting fixed. And so, for example, if we assume sort of a very standard homogeneous Poisson process, the reporting delay is going to have mean 1 over lambda. And for example, if some incidents have a low enough reporting rate, they may never be reported. And I just want to point out that heterogeneity in the reporting rate is not necessarily a bad thing. For example, with the Parks Department might actually want more dangerous incidents to be reported more quickly, right? So if a tree is about to fall down on a power line and take out, power for an entire neighborhood and like, potentially cause harm to people, then like you want that to be reported as soon as possible so you can address it immediately. If on the other hand, a tree is about to, is like slightly overgrowing and cracking the sidewalk, you don't maybe particularly care if you find out about it today as opposed to 2 weeks from now. But on the other hand, there is this concern that neighborhoods are heterogeneous, are like differently using the 3-1-1 system. So for example, there might be a concern that richer, more educated neighborhoods are are more aware of the 3-1-1 system and more trust in government, and so are just using the system a lot more. And if that's happening, then that's a bad thing, because that means that they're also getting better government services, because reporting behavior directly translates to who gets government services. Okay, yeah. So the question, what we're going to try to do first, I'm going to present a method for, and then take it to the parks data, is trying to identify these reporting rates as a function of the type. And I just want to briefly in the language of the model, repeat what I said earlier about potential other methods that one could go about doing this. So for example, the naive method, to solve, not the naive method, it often ends up being fairly sophisticated, but the standard method to solve this benchmark problem is to try to get a separate estimate of ground truth. So let's set that aside. So let's consider the following method. let's count the number of unique incidents that I observe for each type, and then I just compare those numbers for different types. And if the ground truth rates are equal, then I'm going to directly if big lambdas are equal for the different types, then this method is going to roughly tell me little lambda, or at least it's going to tell me the percentage of things that are reported. It won't tell me anything directly about reporting delays, but it will tell me something about unreported counts. And what prior work ends up doing is either just assumes that incident rates are identical across locations, or tries to find proxies for the incident rate. So for example, count the number of trees, their size, the species, use active inspections, and so on. But what we want to do is directly try to find little lambda of theta without necessarily trying to go through big lambda of theta. We're trying to go through the incident rates. Okay. So what's the first insight, the first idea in the paper? It's what's called the missing species idea, which is that duplicate reports about observed incidents tell us something about the reporting rate. So as intuition, let's pretend that we observe every incident and that we also observe the birth time and the death time. So let's assume that these dashed lines are actually observed. And then the number of reports is, in the model is just distributed Poisson at rate lambda of theta for this time duration. And so if we have a bunch of data about these incidents and these time durations, then we have a very standard Poisson rate estimation problem, where my estimate of little lambda of theta can just approximately be the number of reports I see of that type over the sum of the reporting intervals for that type. The problem, of course, in this model is that we don't observe the duration TI, right? We don't observe the full time, even for incidents that we observe, even for incidents in which we've got reports, we don't observe the time interval that, when the incident happened, and then, we potentially observe when it disappeared, but not always. Okay, so there is a question in the chat that I'm going to answer. Feel free to ask other questions as well while I'm reading this. Okay, so the question is the statement that higher reporting is associated with higher fixing of problems an assumption or observed? For example, if problems in higher socioeconomic areas are fixed more often because they're high socioeconomic and not really related to number of reports. Yeah, so I definitely do not want to assert anything about this relationship, right? In this talk and this work, we don't assume anything about the relationship of reporting behavior to higher fixing of problems right now. We're actively working on the downstream parts of this pipeline. So I don't want to make any strong empirical statements right now. But I maybe as a motivating observation, suppose the department is just responding to incidents on a first come first served basis, or responding to them in priority queue depending on the severity of the reported incident, but otherwise in a first come first served. So then delays in reporting and differential reporting is going to directly translate to downstream work getting done. Now, as the question implies, it is possible that the Parks Department is already correcting for that, that sort of thing in their current behavior. Talking to them, it's not clear that they are. The priority queue model is approximately what they're doing right now. But I don't want to make any strong empirical claims yet about downstream inequity. Okay, if there's no other questions, I'm going to move on. But yeah, so just as a reminder, what I just had on this slide is if we observe the entire reporting duration. So if I told you the length that the incident was alive, then this is a very trivial, statistically, empirically, it may not be trivial, but at least theoretically, it's a very trivial Poisson rate estimation problem. And so the name of the game is, even though we don't observe this interval, is to try to find an alternative interval in which we can declare that the reporting behavior within that interval is still Poisson. And so let me give you two attempts to do, maybe the first two naive attempts at doing this. But then maybe give you problems with those naive attempts. So for now, for the purpose of this slide, let me just assert that the start of the interval in which I'm going to start measuring sort of reporting behavior is just the time of the first report. In a few slides, I'll give you maybe why I did that. But for now, let's just say that I'm going to start counting the number of reports at the time of the first report. And then attempt number one, maybe the most naive thing possible, is that I'm going to say that I'm going to count the number of reports in between the first report and some time period t afterwards, right? Some fixed time, like 10 days or whatever. And then, this interval is now t. And then, so in this example that I have, for example, you have two reports in that time period t after the first report. And so from just this data set, my approximation, my estimate of little lambda of theta is just going to be 2 over t or 2 over 10. The problem with doing this is that incidents are alive for very different amounts of time, right? So for example, and so this is just a histogram of how quickly things get inspected, sort of in the data set that we had. And as you'll see is, things that are hazards are inspected and fixed by the Parks Department very quickly. And so the time that they're alive, the time that any report might come is only going to be a day or two or a week. Whereas things like incidents that are alive for that are like very minor might not get fixed for hundreds of days. And so they're going to be, you might observe reports for them for a very long amount of time. And so if you just have a fixed time duration t, then you're going to heterogeneously bias your estimates downwards, because you're going to sort of try to use a reporting interval after reports no longer occur. Okay, so what's a second attempt? A second attempt is just to use the time of the last report, right? So just count the number of reports that happened in between the first report and the last report. And so in this case, it would be 1. And my estimate for lambda of theta would be 1 over b minus a. The problem with this is that you're systematically excluding time in which you know that the incident was alive, but no reports were received, right? You're systematically sort of excluding the time after the last report and in which the incident died. And so this is going to bias your estimates downwards as well. Okay, so those two naive methods didn't work. And so let me maybe back up and talk about the task again. The task is to find a time interval for each incident at which sort of you can be sure that reports were happening and in which reporting rates are Poisson. And so we have the following theorem. It's not a groundbreaking theorem or anything. It's just a sort of a translational theorem for the model. And in particular, what we end up needing is the following. First, of course, maybe trivially, we need the interval to be within the birth and the death period, right? You need to start counting the number of reports after the incident happened, and you need to stop counting before it died. But then you also need both A and B to be stopping times. So what that means is conditional on the events up to that time. So conditional on whatever you've observed before time b, for example, you need A and B to not be dependent on the future. So not be dependent on sort of events after time A or B, and also need to be independent of the reporting rate. And what I just want to point out that the fact that A needs to be a stop, with the fact that like A being a stopping time is sufficient for A is like a trivial sort of consequence of the memoryless property. B is as well, but sort of what sort of surprised us was we couldn't find any. So if people have pointers, we're more than happy to see them. What surprised us is that we couldn't find anything in the literature in which sort of, you have a data set where it's like the length of the observation interval that you see is dependent on sort of the data itself. And so you need to do that correction in your Poisson process. And what I want to point out here as well is that it's completely fine if B is dependent on the data. So for example, if, it's completely fine for things that are hazards to be inspected and sort of like for that to have a much shorter time period. Or it's even fine that B is dependent on the number of reports you've seen so far. It just can't be dependent on the future. Okay, so how do we use this theorem in our application? Well, first I want to just observe that the best choice to start the interval is the time of the first report. So why is that true? Because the time of the first report is the first time you know the incident exists, right? So it's guaranteed that the incident has happened already. So it's guaranteed to be above the birth. It's guaranteed to be below the death because it just got reported. And it's of course a stopping time because it doesn't depend on any event after that time. It just depends on an event that happened at that time period. And so what about B? What about the end of the time period? So what was wrong with our prior two attempts? What was wrong is that they each failed one of our conditions. So if you just do a fixed time duration of length T, then for many incidents, B is going to be after the death, right? So if you do B equals 10 days, it's going to be after hazards already got fixed. And so you're going to be sort of systematically biasing those estimates downwards. If you use the time of the last report, that's not a stopping time, right? The fact that it is the last report depends on the future information that you're not going to observe any more reports. And so what we end up using is, so what was wrong with this fixed T is that it wasn't dependent on the data, right? That you weren't sort of using a smaller time period T for things like hazards or the things that were more serious. How we fix that is we end up using the minimum of this time period T and the inspection time. So, so why is the inspection time a stopping time? Is because it sort of, they're going to decide to inspect as a function of what are the report characteristics, but the report characteristics are known by up to that time. And, the parks department can't tell the future. They can't tell how many reports are going to come in the future for that incident, conditional on the characteristics. And so, and then what we would also hope is for the most part, sort of, talking to the parks department, they do end up inspecting something before it naturally resolves. So we can't guarantee in the data that it happens before the death time, but sort of we're fairly certain that it does most of the time. Okay, so then the method should be fairly straightforward. For every incident I of type theta, we're going to construct this interval AI, BI, and just count the number of reports inside. So in this example, we're going to have just one report inside the interval. As long as B is an underestimate of the time of the death time of the incident, then the number of reports is going to be Poisson inside this interval. For example, if we assume an homogeneous Poisson process, then the number of reports is just Poisson of lambda times B minus A. And for those of you who haven't seen Poisson before, sort of maybe I should have said this a while ago, but like the way to approximate it in your head is just the number of reports you expect to see divided by the exposure time, so divided by the length of the interval, has mean lambda, or sort of some distribution around the reporting rate lambda. Okay, so if we assume an homogeneous process, Poisson process, then we would try to estimate an equation like the following. But we can do all sorts of other things. So for example, it turns out in our setting, something called a zero inflated Poisson model ends up being a very good model of the world, which is we first flip a coin to see if we're going to get another report, if we get a second report. And then if the coin comes up a certain way, then it's going to be distributed according to a Poisson process. Okay, and so what I did so far is for a fixed type theta. The problem in our setting is that we have very high dimensional type, right? So for example, if we include location, we could have up to sort of like 2,000 census tracts in New York City. or over 2,000 census tracts. And so what we end up doing is we end up doing Poisson regression. So we say that sort of the reporting rate lambda of theta is just sort of a function of sort of, the incident characteristics times some coefficients. And then we're going to try to estimate these coefficients. So for example, the fifth dimension of theta could be the height of the tree. The seventh dimension could be, an indicator that it's in one of the census tracts, like which census tract it's in New York. And then for the models that we have sort of these census tracts, so there's over 2,000 census tracts in New York City. Each census tract is like on the order of a neighborhood or something. The type theta can sort of will contain an indicator for this tract. And so we're going to be super high dimensional here. And then sort of in this in those regressions, which I'll show you the results for in a little bit, then each tract, sort of the coefficient for each tract is going to, we're going to apply some spatial smoothing in the model. So we're going to constrain each coefficient to be sort of related to its neighboring coefficients. This is often used when, for example, you have less data and some this is not quite a hierarchical Bayesian model. It ends up being sort of a spatially smoothed Bayesian model. And it's very useful when for some census tracts, for example, we have a lot of data, and then for maybe other census tracts, we don't. So there's a question about sort of using a gamma distribution here and sort of taking advantage of like conjugacy and so on. So yeah, so when we actually started this project, we did actually we did try going down that route of using sort of an empirical Bayesian approach, where we sort of tried to learn these Poisson parameters drawn from a gamma prior. I'm happy to talk about this offline, but for a few reasons, we ended up abandoning that empirical Bayesian approach and going for like a fully either hierarchical or like this like spatially smoothed Bayesian approach. Okay, so that's sort of all I have for the method. Hope sort of the high level method was fairly clear. And then now I'm going to go into sort of actually applying it in our setting. I know I have, Manchi, about how much time do I have left?
About 15 minutes.
Oh, okay. Great. Okay, so maybe I'll pause for a second just to see if there's any other questions about the model or the methods. Okay, so now let's use this method to understand reporting behavior in the New York City 311 system, in particular to the Parks Department. Okay, so the data we're going to use is like mostly public. So New York City is probably one of the leading cities in terms of an open data law. There's an open data law passed about a decade ago, which most agency data is just on a website that you can see, you can just go to right now and download this data. And it actually gets live pushed every night. So you can download all 20 million requests in 311 for the last decade, and then every night it live pushes. But anyway, so we're using mostly public data, but then the Parks Department augmented it for us with internal data on inspections, work orders, and anonymized caller information, which I'll describe how we use in a second. Okay. And so for this department, so we observed about 200,000 service requests over a 3-year period. So we used June 2017 to 2020. Of these, about 140,000 correspond to service requests that were inspected, corresponding to about 100,000 unique incidents. And so there is a decent amount of duplicate reports made about the same incident. And then we have quite rich covariate data for each incident. So of course we have the location, so we have the stated latitude, longitude, and we can map that to a census tract. We have the characteristics of the report that the person filing the report made. So things like the category, like hazard versus side direct damage and things like that. We also have free text that we haven't used yet, but one could imagine using the free text box as well. And then if it was inspected, we have what the actual forester sort of said about the incident. So they assign a risk rating for like how risky this incident is, which like leads to like prioritization of work orders. They also give us the tree ID. And so we have like the species of the tree, we have the size of the tree, and so on. And then we have like a condition of the tree as the inspector wrote it. Okay, so I want to briefly, I don't want to spend too much time on this, but maybe like a minute or two on there's a few sources of statistical bias due to how the data differs from the model that I presented. So the first one is, so, you know, Poisson models, Poisson processes tend to be a fairly good model of the world, except it imposes a fairly strong assumption, which is that reports are independent. So conditional on me telling you that a report happened, that doesn't tell you anything about when the next report's going to happen. And so that doesn't, like, you know, there's no, like, that model is not believable if like the same person is like, you know, every morning is going to be like, the tree in front of my house hasn't been fixed yet, I'm just going to call every morning. And, you know, if they just call on a cadence. And so we need to filter out duplicate reports made by the same person. And so we end up doing that. So we end up sort of the Parks Department gave us anonymized data on who was actually the one to file the report, and our filtering out is robust to, like, you know, filtering out everyone who didn't give that information and so on. But yeah, so we need to do that, and that ends up not changing our results any. It makes the confidence intervals a little wider because we have less data, but otherwise it's fine. Maybe the bigger source of bias, but that we also believe is quite small, but there's also nothing we can do about it, which is the Parks Department only marks duplicate data for the things they end up inspecting, right? So they the forester is going to go in and like mark like these 5 reports belong to the same incident only if they actually end up going out and like inspecting that incident. And so we end up only being able to do the analysis on the inspected set. I'm happy to talk about this more offline after I tell the results, but we believe that the resulting generalization bias is quite small because of this factor. Okay, so let's get to some summary statistics about the data set. So what I have here is just the histogram of what that duration, what that interval, the Poisson intervals that I end up using for the estimation end up being. And so we see here that there's quite a lot of heterogeneity, right? So like for some incidents, I'm only gonna I'm only gonna look at reports that happen like 1 day after the first report. For some incidents, I'm gonna let it go for 100 days. And so I have like a big heterogeneity. So I really did need to sort of look at the inspection time to capture the heterogeneity and how long incidents are alive. And then the second one, which is hopefully to convince you that reporting behavior is mostly Poisson, is that this is the number of duplicates of reports we observe in the time period that we look at. And so the y-axis is on a log scale. And so if it's Poisson, you would expect to see a linear decay on the log scale. And like that's basically what we observe. There's some funniness at, there's more zeros than we would expect otherwise. And that's consistent with the zero inflation model that I mentioned. Okay. I don't want to talk about these plots in detail, but sort of what this is just telling you is after the first report, or after the how long did it take for the first report to come in after the 0th report? So like how long did it take for the first duplicate report to come in? How long did it take for the second duplicate report to come in, third, and so on? And what's maybe the only takeaway here is that these are like fairly linear plots, right? And so this actually surprises quite a bit. What this is telling us is that reporting behavior is surprisingly Poisson after conditional on the number of reports. Reporting behavior is surprisingly homogeneous. And so like we're fairly comfortable just proceeding with estimating homogeneous Poisson processes. Okay, so let's go to our results. And so the first result I'm going to share you is maybe the good news, which is that reporting behavior is fairly efficient. So in particular, so remember that we estimated coefficients for that feed into the reporting rate, where these coefficients could be on things like incident characteristics, report characteristics, and so on. And so these are this is just a subset of the regression table. I didn't want to show you the full regression table, but the full ones in the paper. But what this is telling you is that reporting rates are higher for like the things that are more important. So if the first reporter categorized something as a hazard, we have a higher reporting rate. I'll like translate what these coefficients mean in a little bit. But if if things are like pruning requests or something that's just affecting like a root sewer, like a tree is cracking the sidewalk, then we have lower reporting rates. But this is like exactly what we want, right? And the same is if the inspector found that the tree was in like excellent or good condition, we're going to have a lower reporting rate. But if the inspector said that something was of high risk, we're going to have a higher reporting rate. So this is all like mostly good news and should hopefully provide some confidence that the method is working, right? Like this is all exactly in the direction that we would expect. Okay, so now for the bad news, which is so we have the same regression, and we kept the incident characteristics, but now we also added a bunch of indicators for each census tract in New York. And what we found is that reporting behavior also varies quite substantially by neighborhood, even conditional on the incident characteristics. So what this map is showing you is the lighter colors are higher like census tract coefficients. The darker colors are the lower census tract coefficients, so like lower reporting rates. And the first thing to notice is that the difference in reporting rates between census tracts is on the same order as the difference between hazards and like less it's on the same multiplication, yeah. So like it's like the spread of coefficients is similar to the spread of coefficients I had on the same previous slide. So we have a lot of spatial heterogeneity in how quickly things are being reported. And for those of you who might be familiar with New York, you might observe that the census tract coefficients correlate with socioeconomic characteristics of the neighborhood. And so we can do this in a few ways. You can, for example, just regress these coefficients with census data, population density, of course, but also wealth, education, ethnicity, and so on. And what we unfortunately find is that reporting behavior does vary significantly by socioeconomic characteristic. And so in particular, so certainly, yes, denser neighborhoods end up reporting more. So, higher population means more reporting. That's exactly as expected, but also areas with higher average incomes, areas with higher average education levels also report at significantly higher rates than do other neighborhoods. And maybe last few minutes on this, just to contextualize these reporting rates, because you're probably like me, where you don't actually know what these coefficients mean. So let me just translate that into actual reporting delays. So implied by the coefficients. For trees that are hazards, so consider an incident that's a hazard in poor condition and in high risk. On average in Manhattan, we would expect to see a report with a delay about 2.5 days. In Queens, which is another borough in New York, we would expect to see 4.7 days. For a tree that has some tree damage and it's in poor condition, we would expect to see our estimates imply a delay of about 15 days on average and in Manhattan and about 28 days in Queens. For a root, sewer, and sidewalk issue, for something that's cracking this, a tree root is overgrowing and cracking the sidewalk, our estimates imply a report about 100 days after the the crack first appeared in Manhattan, and then about 200 days later in Queens. So the effect sizes are these are quite substantial differences both across types and across locations. Okay, so to wrap up on this paper, what we do in this paper is we develop a general method to overcome the benchmark problem in settings where duplicate reports about each incident. And then we apply it to understand reporting behavior in the New York City 311 system. And we find quite substantial heterogeneity, even after spatial heterogeneity, even after controlling for incident characteristics. And this is more a request for the audience is sort of, we believe that this method is quite general, that like all you really need are tags for which reports are duplicates, and then timestamps for when reports happened. And so, like, you know, we believe that this sort of method can be used for all sorts of things. For example, to like audit software bug reporting. So are certain types of bugs more likely to be reported by the user base than other types of bugs? And definitely, you know, certainly we work with the Parks Department, but you can imagine doing the same analysis for other city agencies or other cities besides New York City. And so please come to me, please talk to me if you're someone with one of these applications or with access to data from one of these applications. Okay, and so that's all I had to say about this paper. Sort of as a last slide, let's like zoom away from the individual trees and like look at the like the big picture, the big forest about sort of for this project. So I'm just going to put up this pipeline that I had at the beginning of the talk again, which is, we have a pipeline from incidents being reported to work getting done. And today I told you just about one piece of the pipeline. But the work now that my group is doing is how do we understand not just the first piece, but the entire pipeline together. For example, what is the real world cost for delayed reports or delayed inspections? Is the agency, so this was related to a question someone had earlier, is the agency inspecting the right reports? Are they making efficient and equitable decisions? And then we don't care just about auditing, about understanding. We also care about intervening, about doing operations, right? So can we optimally reprioritize inspections and work orders, for example? What does optimal even mean in this setting, right? So like, should we care about some incidents more than, sorry, I can't, my son is hitting my eyes. Can't do anything about that in my apartment. So like, what does optimal actually even mean in our setting? Should we care about some reports more than others and so on? And then perhaps lastly is, can we approximate, if we come up with an optimal, an MDP or RL approach to like actually make inspection decisions, the Parks Department doesn't want to maintain some like fancy RL system that we code up, right? So can we approximate optimal decisions with implementable ones? And so these are the sorts of questions that my group is working on now. And that's sort of all I had to say. I'm happy to answer any questions and talk about this work.
Thank you, Nikhil. This is a great talk. I think there is one question in the Q&A.
Oh yeah, that's a great question. So the question is like I said, one of the ways that our data differs from our model is that in our data, reports may not be independent, right? So like the same person can just like spam the 311 system for reports, and like that's detectable, like sort of, or that's somewhat detectable because we can filter that out because 311 logs who's actually calling. But the question in the chat is sort of another type of non-independence, which is, if people like, residents of a neighborhood coordinating on apps such as Nextdoor to all report the same incident, but with different names so that the departments would get to it faster. And so our analysis is certainly susceptible to that sort of coordination. We don't have a way that we can filter it out. And the question in the question in the chat is, can we use Nextdoor or some, like, can we actually go and scrape Nextdoor to try to find out if that's happening? And yeah, I think that's a great idea to consider sort of to increase the robustness of our analysis.
Yeah, thank you. Thank you, Nikhil. I have a question about this deleting duplicated report. So I was wondering, like, I guess depending on the type of incident, sometimes the duplicated report might be useful or relevant. For example, if the hazard tree is just in front of my house, then I guess the person who lives there would report repeatedly.
Yeah, so that's a great question. So I think what you're getting at is sort of reports, and this was part of what I was implying by optimal, which is like we shouldn't think of these crowdsourcing 311 systems as just like people telling us what problems exist. We should also be thinking of these systems as people telling us what problems are important, right? Mm-hmm. So like, you know, there's some text field that says hazard, but if, you know, if someone reports the same thing 5 times and labels it a hazard, that's probably like actually truly more of a dangerous situation than something they reported only once and marked as a hazard, right? Mm-hmm. So sort of the number, like we should be looking at these reports as also a way for you know, people in a city to tell us what's important to them. And I think that, yeah, I think that's a great sort of, we haven't done anything with that yet. That's like certainly like a question I want, that's certainly analysis I want to do. So, you know, if you want to work together on that, I'm more than happy to.
Yeah, I guess also, I don't know if this is true for 311. So I guess these things would be better understood if the data set itself has a closed loop. So for example, if someone addresses it and then reports whether this is really emergency or not, then I think it would help the analysis more.
Yeah, totally. So so at this point, there's both like an operator that you can call if you just like type out 311, but you can also like submit it through an app. And both ways they sort of, they do give you the chance to like put some free text. And so like certainly like it's a lot of fun if you just like load up the data set and just read the free text that people type. And sometimes they like, you know, they do, you know, you have all caps, you have like people like saying this is urgent and so on. And so, yeah, I can imagine sort of an analysis that like sort of, we haven't done anything with the free text yet, but you could imagine constructing a feature and like putting that in the type as well.
Yeah, thank you. Thank you, Nikhil. Thanks for the great talk. Thank you. And thanks, since we're at the top of the hour, so we are going to conclude here today. And thanks everyone for coming to this seminar, and especially thanks Nikhil for the great talk.
No, thank you for having me.
Yeah, thank you. See you.